Okay. It looks fine. Okay. So this is Calc 3, the third video, I guess. And I'll talk a little bit about my notes on the cross product and then an introduction to vector functions and then also the limits. So especially when you're graphing things out, you're eventually going to get something that was usually known in 2 dimensions, but then you have to translate that into 3 dimensions. So for example, you could have a parabola, which is your x and y. So you get something that looks like this, or that depends. But because we have the third component or the 3 dimensions or the z-axis, then you have to translate that into, okay, then if we have an ellipse, or if we have a parabola, whatever, if we were to plot points out, how would that look like? Sometimes it may look like a cylinder, sometimes maybe a paralleloid, something like that. I don't know how to say it. And cones, what there are other things, but typically as I end up coming out of a cylinder. So all right, here we go. So cross product is another way to solve or to multiply vectors in a sense, because that's kind of one of the big things about it, in a sense, is if we were to combine things, how would that end up looking like? So we could have something that we can trace out and eventually have something that looks like the version of it. So previously with a dot product, what you do in a sense there is, I guess I'm not going to go into the projections and whatnot, but more of else in the sense, if you want to get the components of 2 vectors, so what it would be is, let's say if you had a1 b1 a2 b2 and c1 c2, you could do a1 times b1, a2 times b2, and then a3 times b3. What that would be is whatever the components, so whatever the first, if your x, you multiply x values of your second vector, then the y components of vectors, and then the z components of those other 2 vectors, and you add them all together. And the dot product gives you a scalar, so it gives you something that was your original function, but you either grow it or you shrink it or maybe change direction, whatever that looks like. That's what essentially a dot product is, I guess. Hey, you know what? I'll show you just a brief. I don't know. These are properties, and then there's a theorem that talks about the cosine. So, but I already did that one. Yeah. This is very familiar. Oh yeah, projection. So say if you want to push of one vector down to the other, you write what would how much of that vector would be placed onto the one that you want to put into, and then if you want to raise one up, it's okay how much left over is. The way I like to say is either if the vector you want to put on the other vector is bigger, so let's say the vector here is bigger than the one that you're pushing down, you're kind of saying, all right, how much of the original vector kind of left in a sense, and then you can find out how much was added, whatnot. And then if the bigger ones getting pushed up smaller ones, like cool, how much was left over of the vector you pushed up. That helps for me. That's in my sense. I have the theorems here, but this is for dot product. Anyway, return to cross product. The cross product is it's pretty much linear algebra in a sense. So what you do is, for those who know linear algebra, great. For those who don't, I'll just go briefly into it. So what you need to do to find that is you need to find what a determinant of a matrix is. The determinant of matrix, in a sense, is if you were to have a 2x2 matrix, which is you have, let's say these are your 2 values squared up. So actually, let's see if I can show the camera. So, okay, yeah, that looks fine. So your 2, this is trick. So you have a1, a2. So these are, let's say if this was a of 2 of with x and y's, no z's, this would be here and that would be here. When you multiply via matrix, think of it as if you were doing what do they call it, like cross multiplying in a sense, but with here you subtract instead. That's how it would work in a sense. And for 3 dimensions, it's pretty much the same thing, but now you end up doing this y negative and y positive here. I'll find the theorem that explains it. So, but in a sense, that's what happens is when you have two vectors, when you want to multiply those vectors in linear algebra, you end up right then right here. So this is vector A and that's vector B. You break them out horizontally and say, all right, this will be the I and the J and the K. If you watch my other videos, is X, Y, Z. So these are your X values, these are Y values, and these are your values. So to figure out what it is 3 by 3 here or 2 by 3 here, what you do is if you're trying to solve for what your X is going to be, you block out the you block out here, and that's your matrix for your X or for the I in this case. And the reason why is because you're trying to solve things that aren't going to be related to this. Now you have many ways to cross multiply. So you have to say, okay, then how do I not make sure I don't get this mixed up? Because remember, this is 3 dimensional. So you have 3 different, I guess, there's many coordinates of possibility. There's many ways to try and multiply. So it's okay. How do I make sure that I stay on the X? Because let's say when you're graphing now, for example, X, Y, Z, you have to consider 3 points of, okay, how much do I go on the X? How much do I go on? How much do I go on the Z? With the X is already given a place or like a position vector. That's what the I is. It's 1, 0, 0. So it's like, okay, you have that. But what about the rest? So that's why we not aren't part of that to get to XZ. Okay. Yeah, because for those who don't know, if you're just watching this for the first time, those letters I, J, K stand for a vector or an arrow that points in a direction and has a certain amount of length. The I is a vector or an arrow that goes 1 unit to the right from the x-axis. Nothing doesn't anywhere for the y and z. The J, you move 1 up on the y-axis, but you don't move anywhere from z. And then the K is you move up in a sense, or x. Well, since x to the right, so then z, you would move 1 diagonally positive. So let's say if this was the diagonal, as if the diagonal axis would pierce into the screen, you move 1 to me, not 1 away from me. Because if you go backwards, you're basically going into the screen. That's how I would say for 3D. All right. Sorry, I got a runny nose, but and even when you have 2 vectors, you can find the angle between them. So that one's so yeah, that's also part of it. Yeah, I mean orthogonality, or if vectors can be perpendicular to each other, or you can even ask, okay, cool, is there a vector that exists that's perpendicular to it? That's also one possibility as well. Find 2 vectors orthogonal. Yep. I guess for those who are wondering, okay, what's the difference between the dot product, which was the previous one, and this is the cross product, or I like to think of it as multiplying constants or variables to eventually find an answer. Think of it as multiplications on speed or sped, I guess. The dot product will give you a scalar, and the way I would explain here is, if this was the original vector, a scalar, this thing grew, like this pencil grows, this pencil shrinks, maybe it turns a different direction. But sometimes you may end with negatives in there. Most, and yeah, I would say that's probably a good way to describe the scalar. And with the cross products, you would get essentially a new vector. But the typical vectors that maybe I explained in the previous video and I compared to this, is how can I say this? Well, I mean, yeah, I mean, I have a theorem here that explains it, but this isn't useful to explain what I want to say. I would say that with the cross product, it would stretch or squish the whatever the area is, because in typical linear algebra, well, when you do these transformations, what you do is you feel like as if you were what is that thing that not Play-Doh, but it's the noise putty. So you know how when you putty in this direction and then maybe that's the same with those with the matrices. Like you have a certain point in the vector and you say, cool, I want to stretch it up to here. Maybe 3 points to the right, one up, and then maybe you say, oh wait, now I want now with the multiplication of this matrix, now we have to inverse and send it to negative. So it's like, okay, from here, turn it around. So it's kind of with the when you stretch, squish, and then maybe try and do a loop de loop. I don't know, whatever you do with noise putty. That's essentially what I would say is go with cross products. Essentially in 3D is okay. Now you have this area to consider, and you multiply these vectors, which also have area under them. It's okay if you were to multiply these two together. What would happen? Would you stretch? Would you go in a different way, or would you go to zero? I don't know. What happens? That's what I would say. That's what I would say. What goes on? All right. For example, that determinant I showed you earlier. That's essentially what's saying. Okay, if you multiply them, what's going to happen? You stretch, squish, go to zero, flip direction. I would say probably that would be a good way to say it. I mean, these are just examples of, yeah, this is a parallelogram in 3D that I'm looking at right now. This doesn't really, yeah, this isn't necessarily, I guess, the most useful of things because essentially you would have to, I mean, I could tell you, but I just be regurgitating what I said here. So I think it's much better if one experiences this thing. But then again, you would kind of need a little bit of a vectors first. So for something in 3D or like the volume, let's say, or the volume of any 3D is like the base times height in a sense, or the area of the base times height. Similar to what was in 2D where you have, I don't know, squared. It's like, all right, well, it's base times height. So you kind of apply that. But now you consider, okay, this is 3D that we're talking about. So the area of the base, in other words, you're saying, okay, this is the length of how, I guess, big this thing is. Like you're going to go a certain amount. But that base already that's kind of have lengths. And these lengths, or these things that we can make for the base, you can call them vectors in a sense because they have a specific direction to go a certain amount of length. So that's why we might see of an area of a base is essentially your length or your magnitude, whatever your teacher calls it. But that's essentially what it would be. And then also to determine height, the height would also still be unknown in a sense. You would have to draw a couple of extra triangles to figure that one out. But I think that's probably one thing I would say is the height will come more intuitively, but the area of the base is another one. If you were to put a line and then you add an arrow at the ends of it, that would be your vector. And then after that, you'd say, all right, then if these are vectors, then that means this will go a certain amount. So that's your length of the base or your magnitude. Yeah, these are more proofs of how to solve stuff in 3D, but okay. Useful here. Let's see. Well, sometimes, well, I get, yeah, actually, I didn't mention what happens if a cross product is equal to zero. So let's say, actually, let's keep going with the volume. So let's say volume is zero. What you're essentially saying is height doesn't exist. So that means your your three-dimensional object, let's say it's I don't know, a cylinder. It has zero height because you need some magnitude. Okay, your magnitude just can't be zero because then you have basically this over what? I think that's just a line. But think of it as if you were as if I had the book, for example, and I said, all right, I'm gonna squish this to absolutely zero. So make it entirely flat. So you still have magnitude, you still have length, but you just no longer have anything that mm, you just kind of don't really have a z-axis in a sense. So I don't know if you ever get examples where you might have the I and the J. That's kind of what it is, at least in volume terms. Um, so yeah, so that's so let's see. Oh, here's another one that I had to look up, which was because I didn't understand it. So, but when you do a cross product, you're finding an orthogonal vector. So I kind of looked at there. I'm like, why? So why? How? Who cares? So here's the proof. So the proof goes: vector A times vector B is going to be uh orthogonal or perpendicular to the vector A and the vector B. They're both going. So if you multiply the two of them, you're going to end up A and B. So how? So to check if those so the proof is by checking, and what you do to find it, you do the dot product of those two vectors. So the dot product, what you do is you essentially take your first vector, the A times B part, which is what you're looking for, and then you take one of the vectors. You can pick the A or the B, whatever makes sense to you. And then you would do the entire matrix. You would spread it all out and see, okay, what happens. And when you do, eventually you cancel everything. So the dot product is going to be zero. And when it's R zero, at least when you do the dot product, what you have basically said is, okay, there. Think of it like with the cosine pi of zero. Cos So essentially, that's what's kind of going on. Is now you have essentially this thing that doesn't go anywhere on a specific axis. So, which I found that one kind of in a sense where when you're doing the cross product, you're going to look for an author and a perpendicular or orthogonal, and that will always happen in a sense because you are essentially multiplying two of them that already have specific direction. Now you're saying, all right, if we were to find something that is either in between of them or something, hold up, or something that is greater than them, it has to end up that is perpendicular or like this, something that looks like that, compared to what the other two vectors actually. I'm going to find an example that I graphed out that explains that. Jesus Christ, I'm going to need. Oh, I need some holes, whatever. I don't think I went down well. Here we go. Reason why zero is because whenever you have two vectors, you have an angle, and that angle is also considered, but you don't necessarily focus on it when you're doing a cross product. But that's kind of already embedded in there. Is you're kind of saying, all right, if you have these stories are going to end up, and most likely when you do math, actually, you're going to find out that theta is zero, which means that okay, because let's say if I don't know, let's say if it was cosine of zero, you're not going anywhere. Because what's cosine zero? Well, one. So you're gonna just stay here. X value 1, 0. But if you say cosine pi halves, then it's like, okay, what are the coordinates of that? Well, cosine pi halves is 0. So where's pi halves? Oh, well, about here. But then the value of cosine pi halves 0, then it's like, okay, then we need our y-axis. What sign of pi halves? Well, that's 1. So here. So they're so this is a parallelogram. You have these, but you always consider that there's an angle in there, and this is just proof. All of that is proof, which is find the area of PQR. But when you're doing area, essentially, yes, you will eventually find it and whatnot. So, yeah, at least in this case, we had the base times height, which we have two vectors and a sign. Yep. Mm-hmm. Yep. Okay. So I'm just looking at the proof. But there's nothing that much I need to explain. Okay, vector functions. So this one kind of goes now a little bit into calculus of, I guess, calc 3, I guess. This is the real stuff. So right off the bat, there's parametric equation. So whoever's in calculus, you might already do that. So essentially what you have is x and y are no longer possibly independent variables, and those are dependent on a new variable. So typically in calc 2, your independent variables, so things will become something like x of t or z of t, whatever. But now t is that independent variable. So now you can those expressions like dy, dt, dx, dt, because x is no longer that independent variable. It relies on t to get answer in a sense. So okay, but on in 2D you learned that x was f of t and then y is g of t. Then I have for 3 at the third one, which is z is h of t. Just follow sequential of alphabet. And then with vectors, essentially you could just write it the same: f of t I, g of t j, and then h of t k. You can express that as position vector with the brackets. And for t, there's time also too. So let's say typically t is probably time most likely. So sometimes you can have a limited domain, which means that limited domain also tells the direction you're going. Because let's say if it was t, t can only be between -1 to 3. Well, now you know that t has a specific direction. It says you can only go from here to here, nowhere else. Because a vector, you need length and a direction to point at, essentially. You can also find domains of that too. You can also look for what's the domain of of t to see, okay, where do points exist and whatnot. And then you can just plug and play points. You can do that. And then when you stretch initial points, so when you put IP, okay, initial points. Okay, these are just steps for sketching out things in 3D, but essentially what you do is you go how much X direction, and then from there pretend like you're walking on the Y-axis, and then up to your Z-axis. But I don't know. It would take me an hour to, not an hour, but I wasn't meant to teach these things. I'm just explaining things so that I can distill it better for myself. Because I know that when you attempt to teach it to someone else, shit's the fan. So you got to sense. It's like you have to have a deep understanding of it, not just memorize all this X, Y, Z. But all right. Where were we at? Okay. Oh, and when you're also doing the vector functions, sometimes you will have not x y z. You will say, oh well, x can be 1 plus 16 over 3t, something like that, or 5 minus 3 half, and then that thing would be your x y z. And then you say, cool, is there a way I can express two of them or three of them in just one equation? So here's one. So the vector RT, so t is the independent variable, and that is equal to the x value is 1 plus ti, the y value is 2 minus tj, and then the z value is 3 minus 2tk. Then you have to ask yourself, okay, where can I plug in this everywhere? And 1 plus t, 2 minus t, 3 minus 2t, that's a line. All you have to do is simplify, and then you can find out, okay, then this goes straight. There isn't anything left over in a sense. Like t plus 1, like 1 plus t is just t plus 1. So whatever your value is, you just move on, and then you can plot it, and you realize, oh, it's a line. So, but now you have to know where to plot it in a sense. Well, what you can do is, let's say t is x minus 1. What you have to say is, okay, how do we define t? So x equals 1 plus, that's what that x is. Now you have to solve for t. So t is x minus 1. Cool. So then you say, right, if that's true, then I want to make sure that every single value that I get, how can I get to make sure that t get me at least, let's say, how can I get one of the points, x, y, and z, to be 0 so that I have to do the least work possible in a sense? Because that would be good. That'd be good if we don't have to worry about it. So you could say, all right, if t is equal to 0, what value of x, z do I need to get to make it 0? But then you can also ask, cool, if my x value to be 0 so that I don't have to do that much effort, then what value is to go in for that? But then that means that value has to go in for every single thing, in a sense. So say if t is equal to x minus 1, and if you wanted to set t equal to if you wanted to set x equal to 0, you would plug in 0. Cool. But then that means your t would be -1. So it's like, okay, so if your t is going to be -1 for everything else, so for example, t minus t, if your t is -1, so -1 equals, then what's your 1? Okay, cool. That would be 3. So, but you don't include the negative, it's just 3. And then for the other one, it's -1 equals 3 minus z over 2. It's okay, what do I need to get -1? In that case, 3 minus 5 negative over 2, 1, then -1. So that's how it would work. The plot points there. And then you can go into fancier ways like t squared, t cubed, but that what that would give you is actually, when it's not really a line, you end up getting a parabola and ellipse, something like that. And when you begin graphing that out, you realize, hey, it's a shape. It's a shape in 3D. Okay, and typically most of the time it's probably or something else like. And then limits for functions is probably the easiest thing I've taken so far in these things for Professor Leonard. Limits of vector functions where you would literally write like if it was any regular limit, and I have to consider that okay, this isn't a point, this is a vector, this is an arrow I'm considering, which says if I take it to this value, what not what point, but essentially what vector am I getting out of this? Because you're taking the limit of a vector, limit of an arrow that says you will start at the origin, but you will end up at this place, which is still a vector because position mean your starting point 0, 0, 0 doesn't matter that you go up to this point. So that's what it is. That's when you take the limits of position vectors. So I get you know, I'll show you this one briefly. So here's what so one. This is this is limits of continuity, which just basically says look at your vector, your position vector. Look at the x, y, and z values. Where is it undefined? And then that would be your and say, okay, then the values of t can go into here. But and I'll just show you the domain. So this is a domain problem. It says this is r of t. These are my this the x is the y is the z. So the x value is cosine t minus 1 over t. The y value is square root of t over 1 plus 2t, and then the value is t times e to the negative 1 over t. We're not solving it, we're just asking for the domain. So for the domain, where is it undefined at x? That's at 0. You can't divide over 0. And then for the y value, where is it undefined, or what values can you not put for a square root? You can't put anything less than 0. So it has to be 0 or higher. For the denominator, 1 plus 2t, so what value can we not put in there? Negative 1/2. Okay. And then for t times e to the negative 1 over t, we have a fraction on the top of the denominator. Sorry, on the exponential function. And if we throw in 0 over negative 1 over 2, we're going to get an undefined. So that doesn't work either. So what we're saying is for x, we cannot have 0. For the y value, we cannot have negative 1/2, but we have to be equal or greater than 0. For the z value, we have to be greater than 0. Or for z value, you cannot be 0. Sorry. What that means is okay, negative 1/2 is less than 0 anyway, and all of them have to be either 0 or not 0, so we don't have to worry about negative 1/2. But 2 of the 3 say we cannot be 0. One says, yeah, I can. So you don't include 0 in a sense. Because if one says cannot be 0, then the rest cannot be, because then you'll have an undefined point on your vector, on the position vector. So this would be 0 to infinity, not including either. So that's how it would work. But I guess just to wrap it up, here's one. So as the limit as t goes to 0 from the right, so 0 plus of cosine t I plus tangent t over tj, and then plus t over ltk. So if your trig, if you're an Hopital's rule, then you're going to go in a sense. So basically what that is can you just 0 for any of them, see if it works? For cosine t, sure, that's cosine of 0 is 1, so that's okay. Tangent t over t, what you would need to do, you could do a Hopital's rule, or you can do trig at least. I did a Hopital's rule because I don't know, that was the first I thought of. You do secant square t over 1 for tangent t over t, and then secant squared over t is just 1 over cosine. So you plug in 0 for that, that's 1 over secant squared of 0, that's cosine squared, 1 over cosine squared, so that gives you 1 over 1, so that's also 1. And then t times ln of t, that would be, if you throw in 0 immediately from the right, you would get 0 times negative infinity. So that's a indeterminate form, so you can use the Hopital's rule if you want. That would give you negative t after you do all the simplification. You get negative t. But when you plug in t for 0 positive, that's just plus 0. So you have 1 for your x value, 1 for your y value and 0 for your z value. You can do brackets 1, 1, 0. You can just do the I plus considers a k because there is no value for k. So yeah, that's basically it for this one. So for me, I know I will do more practice problems on all these things because everything I just mentioned is just pretty much the basics, if we're being honest. Sure, there are shapes and whatnot, but most of it just relies on these vectors, and we do derivatives, integrals, and whatnot with these vectors and shapes too. So I know that will probably be the bulk of it because my classes start in a week and a half. So I know that just getting more into the grip of what are these vectors kind of manipulated to my own will, and then derivative, maybe I'll try and get derivatives in, and then a basic introduction to the double integrals, hopefully. But as long as I'm ahead of the game, I'll win. So, and then I'll keep working on the distill minds thing. So it's I'm learning at 1,000,000 miles per hour in a sense. But hey, that's the figure it out game. So